Schrodinger bridges and entropy regularized optimal transport, and we are going to talk now about duality to start with. By the way, I should also say that next week we have the Thanksgiving break. So I think, so next week we have a class on Monday. This is taught by Young-Hin, but then there are no more classes on Wednesday and Friday. And the week following that is our final week here. Okay. So we're going to talk about, so we started discussing this entropy regularized topic. So let me just recall again what the problem was. So I'm given two probability measures. So given mu and nu, these are probability measures V2 on RD. I'm going to assume that these are absolutely continuous. And then I'm looking into this problem of EOT, epsilon, mu, and nu. And I'm looking into this problem that this is the argmin, sorry, just the mean. The inf over all couplings of mu and nu, 1/2 norm of y minus x norm squared d gamma plus epsilon entropy of gamma. All right, okay. So this is related to a Kullback, I mean, by simply multiplying by this with epsilon, you can relate this to a Kullback-Leibler minimization problem. And this you have also described this, that this is a Kullback-Leibler projection problem. That you look into the R epsilon of xy to be 1 over square root of 2 pi epsilon to the power d, e to the power minus norm of y minus x norm square over 2 epsilon. Now this is a density of not a probability measure, but a sigma finite measure. Okay, so let me just use small r here. Just use small r here. Okay, so this is a density of a sigma finite measure. The sigma finite measure is representing the joint distribution of a Brownian particle at time 0 and epsilon. This is a joint density of B0, B epsilon, where B0 is being sampled from the Lebesgue mid density, and then BT is just Brownian motion. It's standard Brownian motion. In RD. And so instead of looking into this EOT problem as it is written here, we can also write this as the infimum over gamma in the set of all couplings of mu and nu. I look into minimizing Kullback-Leibler of gamma with respect to R epsilon. Okay, and so that's the Kullback-Leibler projection problem. And once you do this, this times epsilon times this, or I can write this as this is 1 over epsilon, the EOT epsilon mu to nu. The minimizer is called the Schrodinger bridge.
Sorry, Professor.
Yeah.
So is that BT or B epsilon? BT is standard for an emotion of B
So
epsilon
BT is the process,
Mhm.
and I'm evaluating BT at 2 time points, 0, time 0, and time epsilon.
Oh, I see. Okay.
And so now we're looking into the joint density of the two.
Okay. Okay, thank you.
Yeah. So this is the minimizer is the Schrodinger bridge. So Schrodinger bridge at temperature epsilon between mu and nu. All right, okay. The first thing that we are going to do today is to prove the following duality theorem. Which is duality, which says that this object, that this infimum over all couplings of mu and nu, Kullback-Leibler gamma with respect to R epsilon, this is equal to the supremum over phi in L1 of mu, psi in L1 of nu, integral of phi d mu plus integral of psi d nu minus integral of e to the power phi x plus psi y dr epsilon plus 1. And that's the theorem. So it's a supremum over all integrable functions with respect to mu phi and all integrable functions psi with respect to nu. And what I'm taking a supremum over, which is a linear function first, which is integral of phi d mu plus integral of psi d nu. And then what I am adding to it is minus the integral of e to the power phi plus psi, integral with respect to r epsilon, which is this joint density I've written down, plus 1. Okay, who can tell me how is this different from the regular Kantorovich duality? Before I give a proof of this, the question to ask is how is this different from Kantorovich duality? Any answers? What do you think? Do you guys remember the Kantorovich duality problem? The Kantorovich duality formulation of optimal transport? How is this different?
So there is an extra exponential term there?
There is an extra exponential term here. Very good. So Kantorovich duality problem would say that if I look into W2 square between mu and nu, I'm going to still call it 1/2. Then I would see that this is the supremum. I have this integral of phi d mu plus integral of psi d nu, and there is no other exponential or constant or anything. So that term is extra. What else?
There is a one, but in Kantorovich duality, there is no constant apart from the integrals of the phi.
Right. So that's exactly what I'm saying. So we don't have the exponential term, we don't have the constant term in Kantorovich duality. We only have the linear terms. That much is fine. What else is different? There's another key difference here.
Boundedness of the from above by the cost function.
Very good. So in the Kantorovich problem, what you really require here is this phi x plus psi y should be less than or equal to cxy, which in this case is 1/2 norm of y minus x norm square. So the supremum is not over all arbitrary functions phi and psi, which is in L1, but all those functions phi and psi, which are constrained to be bounded above by the cost function here, which is the 1/2 norm of y minus x squared. This supremum for the entropy regularized cost function has no such constraint. It is completely over the supremum where all phi and psi. So let's write this down again. So what I'm seeing here is that this is equal to the supremum over all phi and psi. I have this integral phi d mu plus integral psi d nu. And then I have integral of e to the power phi x plus psi y minus 1/2 norm of y minus x norm square divided by epsilon dx dy, right? Because that's a joint density, plus 1. So how do you think are these two related? That this constraint over here, which is about a constrained set of functions, but it has only linear terms, and this optimization over here, which is our unconstrained set of functions, but it has this exponential. How do you think these are related? Do you think that you should expect reasonably that as epsilon tends to 0, the unconstrained problem should converge to the constrained problem? What do you think is the relationship? Sorry, this is a 1/2 epsilon here. I did something wrong. Sorry, I did something wrong. Hold on. Oh, this. Okay. So the thing that I did wrong would be here, putting an epsilon here. Okay, putting this epsilon here. I think this is correct now. No. No, I think this is correct now. Yes. We'll see when we do the proof if I missed a constant. The thing to notice here is that look into this term. Look into this term over here. If the function phi x plus psi y plus psi y, there are two things that can happen. If this is less than or equal to 1/2 norm of y minus x norm square, then what do you see here? What you see here is that this term over here, which is the difference over here, becomes negative. And when you divide by epsilon and you integrate that, it becomes exponential of a large negative number, which means that this goes to very close to 0. So if a function is fully satisfying this constraint that phi x plus psi y is less than or equal to this cost function, as epsilon goes to 0, that exponential over here is just dropping out. Right? On the other hand, if phi x plus psi y is somehow larger than minus 1/2 of y minus x squared, so somewhere that sum is actually larger than that, and then what happens is that when you exponentiate this, you get e to the power a very, very large number. And then e to the power a very, very large number, when you did this e to the power a very, very large number, it will comes at a negative sign over here. And so that cannot be the point where the supremum is achieved, because you get a very large negative number. And so effectively, the supremum will be attained over the set where you have phi x plus psi y is less than or equal to 1/2 of norm of y minus x squared for all x and y. Does this make sense? So let me repeat again. If phi x plus psi y is less than or equal to 1/2 of norm of y minus x y, let's say for all x and y, all such pair, which means it's in this set, then I have an exponential of phi x plus psi y minus this difference. And so that difference is negative. Now, if I have this negative term, whatever that small negative term might be, maybe minus 0.01, when epsilon goes to 0, I divide by epsilon, it becomes a very large negative number. When I exponentiate this e to the power this large negative number, this whole integral is going to vanish. It's going to go to 0 as epsilon goes to 0. And so essentially you're left with just the linear terms. Now let's consider functions for which this is not true. And in fact, there are points x and y. In fact, a positive measure of points x and y where this inequality is reversed, where phi x plus iy is larger than 1/2 of norm of y minus x squared. In which case, this term over here, this is positive. If this is positive, I divide by epsilon. As epsilon goes to small, this becomes a large positive number. I exponentiate it, becomes a very, very large positive number. I put a negative sign in front of it, it becomes a very large negative number. So that cannot be where the supremum is achieved, because it's just dragging the whole thing down to negative infinity. So this exponential is basically doing a soft constraint where you're effectively eliminating all functions which do not satisfy this hard constraint of phi x plus psi y is less than or equal to cxy. Are you with me? Do you understand this? Do you guys understand what I'm saying? Okay, good. All right, okay, so let's try to prove this. I'm pretty sure I've put the epsilon somewhere wrong here. Okay. Now I realize where the mistake is. Okay, so where I put the argument is correct. The mistake is over here. I should really be putting here. Okay, I'm going to make this change. I'll explain to you what I'm doing here. So this I will put as epsilon here. This I will put as epsilon here. So it's phi over epsilon, psi over epsilon, and this everything here. I'll explain why. This is just a scaling. Okay, this doesn't change the problem. I'm always doing with phi over psi. This doesn't really change the problem. What it does here is this following. And so let me go back here. So as epsilon goes down to 0, I expect this problem, as epsilon goes down to 0, this problem to converge to W2 square mu nu. Right? Because this is a term which is vanishing. The remainder term is exactly what I'm converging to W2 square mu nu. Now, I already explained that the minimizing of the relative entropy is 1 over epsilon times this EOT problem. And so what I should expect is that when I multiply by epsilon here, then this exactly is what is happening. So epsilon times the infimum of relative entropy is the EOT problem, which means epsilon times this is what should converge to W2 squared, or rather 1/2 W2 squared. And so if I have to compare the duality of the two, I should be comparing the duality of this guy and 1 over 2 epsilon W2 squared. Make sense? Because they are epsilon scaling of each other. And that's really what I was trying to say, because that would give me this epsilon, and then the rest is consistent. Okay. Honestly, you should multiply by epsilon on both sides to compare the duality, but okay, that you understand what I'm trying to say here. Does this make sense what I'm saying? There's an epsilon scaling that I was applying it wrong to compare the two terms. Okay, let's try to prove this duality. Okay, so again, if I want to compare directly with 1/2 W2 square and this duality, I would multiply everywhere by epsilon. So it would be epsilon times this function. These epsilons will cancel out, and I would have epsilon integral this epsilon here. That's the only difference. All right, okay. So let's go into the proof of duality. So the first step of the proof of duality used to use something called Fenchel's duality. So we will use Fenchel's duality. What does that mean? It means that these two functions, fx, which is x log x minus x for x non-negative, and infinity for x negative, is convex dual to f star of y, which is e to the power of y, or y in R. These two functions are convex dual of one another, x log x minus x and e to the power y. Why? Well, just verify it. So what do I have to check? I have to look into the supremum over, let's say, x times y minus e to the power y. And I take a supremum over y, and I have to verify that this is exactly x log x minus x. I need to verify this. That's convex conjugacy. Now, apply first order condition to this. So take gradient derivative with respect to x. X equals to 0, and then put it equal to 0. Sorry, derivative with respect to y and put it equal to 0. So what do I get? I get x star where, so x is given. X is equal to e to the power y. And that would give me, for the optimal value of y, the optimal y is nothing but log x. And so if the optimal y is log x, then you just substitute it over here, and you get that this is x log x minus x. Good, so it's just a direct verification that the functions x log x minus x and e to the power y, they're convex conjugates of one another. Clear? As you learned from the beginning of this course, convex conjugates satisfy this formula. Hence, for all x which is non-negative and y that is positive, I get that f of x plus f star of y must be greater than or equal to x times y. This is just convex, this is just conjugacy. So what does that mean? That means that if I look into x log x minus x plus e to the power y, this must be greater than or equal to x times y. By the way, this is what is called Fenchel's inequality. This is true for any two pairs of convex conjugate functions. In particular, I get x log x minus x plus e to the power y is greater than or equal to x times y. In other words, I would get that x log x is greater than or equal to x minus e to the power y plus x times y. Okay, this is for all x which is non-negative and all y which is strictly positive. Sorry, all y in the real line, not strictly positive. All x that is non-negative and all y that's real here. Okay. Now, what am I going to apply it to? I'm going to apply this to, so take x to be d gamma star dr epsilon, which is this thing, which is over here. So gamma star, okay, I have to write down what this gamma star is. So gamma star is my Schrodinger bridge. So the density is gamma star. Or of this gamma star epsilon xy. This is the density. Okay, so apply this to d gamma star dr epsilon. Right? And what am I going to take y to be? So y is going, so this is clearly non-negative. So gamma epsilon star is the Schrodinger bridge. Schrodinger bridge density. What is my y? My y is any function phi of x plus psi of y for any pair phi and psi, which are this one is L1 of mu. The other one is in L1 of mu. All right. Of course, I'm making a mess of this notation here. I say x and y, but really I'm changing this. So I'm really defining these two things. But nevertheless, what I get from my Fenchel's inequality is that for any xy, I get d gamma epsilon star dr epsilon log of d gamma epsilon star dr epsilon. This is greater than or equal to d gamma epsilon star dr epsilon minus e to the power phi x plus psi y plus x times y, which is phi x plus psi y dr epsilon, d gamma epsilon star dr epsilon. Do you guys follow what I'm doing here? I've made a mess of the notation here, but really what I'm trying to say is that for any x which is non-negative and any y which is real, I get this Fenchel's inequality, which is x log x is greater than x minus e to the power y plus x times y. And now for x, I take this Radon-Nikodym derivative of the Schrodinger bridge with respect to my reference process, my Brownian reference density. And for y, I take this sum of the two functions, phi x plus psi y, for any pair phi plus psi, any pair phi and psi. And then I apply Fenchel's inequality, and I get this line, which is over here. And now what I'm going to do is that I'm going to integrate with respect to r epsilon on both sides. So integrate on both sides. Now, when I integrate the left-hand side, I get exactly Kullback-Leibler of gamma epsilon star with respect to r epsilon. Right? That's by definition. I get from the left-hand side is exactly this Kullback-Leibler. Now, on the right-hand side, I will integrate d gamma epsilon star. I realized my gamma epsilon and r epsilons look very similar. This is r epsilon with respect to dr epsilon. What does that give me? 1. Right? Because r epsilon cancels out from numerator and denominator, and the integral of gamma epsilon star, that just gives me 1 because it's a probability density. I'm not using the r epsilon is not a probability density. That never gets appeared here. That never appears here. Next, I get this is the integral of e to the power phi x plus psi y dr epsilon. And the last term gives me integral of phi x plus psi y. Again, r epsilon cancels with dr epsilon. So this is just d gamma epsilon star. Now over here, I use the fact that gamma epsilon star is a coupling of mu and nu. And so this integral actually separates out. And I get that this is always larger then 1 minus e to the power phi x plus psi y dr epsilon plus the integral of phi x mu dx plus the integral of psi y nu dy. And so I've proved one side of the inequality, that this Kullback-Leibler is always larger than this. Did you guys follow this argument? Okay, good. And so I will be done once I prove the reverse inequality. So for the reverse inequality, I need to come up with one phi star and one psi star. Need to show some phi star in L1 of mu, some psi star in L1 of nu, such that the Kullback-Leibler of gamma epsilon star r epsilon is equal to integral of phi star d mu plus integral of psi star d nu minus integral of e to the power phi star plus psi star x y dr epsilon plus 1. Once I prove that there is for some of one for such this is actually true, then I've essentially proved my theorem, which is that this is true. Again, they ignore these for epsilons here. The epsilons don't matter. The L1 space is invariant whether I divide by every function by epsilon or not. So that's doesn't really matter. Okay. So how do I find such phi star and psi star? Because Ruthendorf's theorem tells me that there exist some such kernels. So I know from Ruthendorf, I know that gamma epsilon star has the following form. Gamma epsilon star times mu x times nu y has the form which is e to the power minus 1 over 2 epsilon y minus x norm square minus a epsilon of x over epsilon minus b epsilon of y over epsilon. I know that these things exist. And so then I can write gamma epsilon star xy as this first part. This is my r epsilon xy. And then combine everything in the second part to write it in the form phi x plus psi y. So phi star of x, psi star of y. So I'm combining a epsilon minus a epsilon of x times epsilon with mu x, and combining minus b epsilon with nu y, and writing them as phi star of x plus c star of y. But that's it. Once I have this, then I know exactly what is the Kullback-Leibler of gamma epsilon star with r epsilon. By definition, this is the integral of the log of the density. So I would look into, so log of e to the power phi star of x plus psi star of y with respect to gamma epsilon star. And so what do I get? This becomes integral of phi star of x d mu plus integral of psi star of y d nu. But what happened to the other terms here? So this is a plus 1. What happens to the other term here? This exponential. Well, if I write down what is this exponential here, this is e to the power phi star of x plus psi star of y dr epsilon But that is exactly gamma epsilon star. So this is nothing but the integral of gamma epsilon star of xy, which is just -1. Because it's a density. And so when I add a +1 to this, I get this is another +1, -1 +1. This is just 0. And so I figured out some phi star and psi star where this Kullback library is exactly this. Again, do you understand this process? Let me again go over the argument one more time, slowly. So I want to prove the following duality theorem, which is this EOT cost function can be seen as a supremum over all L1 functions, integral of phi, integral of psi, minus the integral of phi plus psi over epsilon. I'm just going to erase these epsilons here, because just to keep it consistent with the proof. This epsilon is only needed when you take epsilon going to 0 to compare with the Kantorovich potential. Otherwise, it's not needed. So I want to prove this. So what is my strategy of my proof? The strategy of the proof is to show that the left-hand side is always larger than the right-hand side for any pair of functions phi and psi. And then the second part is to exhibit one pair of functions phi and psi for which this is equal. And that proves that this is the supremum. So how is the first part proved? The first part is first proved by using Fenchel's inequality. The functions x log x minus x and e to the power y, they're convex conjugates. And so I get from Fenchel's inequality, this is true for all x which is non-negative and all y which is real. I applied this x to be the Radon-Nikodym derivative of the Schrodinger bridge with respect to the reference r epsilon, and take y to be any pair, the sum of the functions phi x plus psi y for any pair of functions phi and psi. And then I write down Fenchel's inequality, I integrate with respect to the r epsilon, the reference, and I get that the Kullback library is always larger than the right-hand side, which is exactly what the duality demands, the linear terms, the exponential term, and +1. So that's first. For the reverse inequality, I look into the structure of the Schrodinger bridge itself. And I say that I know the Schrodinger bridge looks like r epsilon of x e to the power phi star plus psi star of y. And if that's the case, I can write down exactly what the Kullback library is. And this gives me the two integral terms. And what happened to the additional terms? The additional terms, they just vanish. Because the negative of the exponential of the term, that exactly gives me 1, because it's the integral of the Schrodinger bridge itself. And then I add to it 1, and I get 0, and so I have this equality. And therefore, I've proved my duality. Convinced? So not a very difficult proof. It doesn't really, it's not nowhere as difficult as functional analytic proof as the Kantorovich inequality itself, which is you have to do some actual in-soup interchange. This is a much more simple proof, just using one application of Fenchel's inequality. Good. But then I've explained why you should expect the duality from Kantorovich inequality to follow from this. One more time, you see that working with the entropy regularized optimal transfer makes your life simpler. Look at the duality proof. Simple. All right, okay.
Wait, sorry.
Yes, sorry, go ahead.
About that. So we did use the fact that we can find these Schrodinger potentials.
Yes.
And that the existence of the Schrodinger potentials, that would require some functional analysis. But
that would require some, yes.
Does that functional analysis argument to show that the Schrodinger potentials exist, would you still say that that's like easier, I guess, than the argument for optimal transport? Because that would be...
Well, the problem will be that, when basically the form of the Schrodinger potentials also is essentially giving you what Brennier's theorem is. In fact, there's a paper which reproves Brennier's gradient of convex functions from the fact that these Schrodinger potentials exist. I haven't gone into it, but you can always argue that these two functions, a epsilon and b epsilon, are convex. You can always argue this. Actually, not slightly convex. If you just turn out this x square and you combine with a epsilon, y square and you combine with b epsilon, you can always argue that these are convex. They're always convex for every positive epsilon. And then you can just take a limit as epsilon goes to 0 and recovers Brinner's theorem from there. So yes, there are multiple proofs to show that these A epsilons and B epsilons exist. As I said, you don't have to do functional analysis. There are multiple ways of arguing this, that this is true. But once you get the form of the Schrodinger bridge, in one soup by taking limits with epsilon, you recover both Kantorovich duality as well as Brinner's theorem.
Wow, okay. Yeah, thank you.
Okay. Any other questions? Okay, there's a paper which does this. I'll post it in the. This is a paper by Mikami. I'll post it on Slack. All right. Okay. So moving on, let's look into the dynamic picture. So a Benamo-Brenier formula for EOT. Okay, so recall what a Benamo-Brenier formulation is. So a Benamo-Brenier formulation is that if I have a W2 square, so I take mu, I take nu, I look into W2 square distance between nu and nu. And now the Benamo-Brenier formulation says that this is the infimum over all rho t vt. So rho t is absolutely continuous between mu and nu, continuous curves joining mu and nu. And vt is a tangent velocity of rho t. And then I look into this integral from 0 to 1. I look into the L2 norm square of rho t dt. And that's giving me my W2 square. This is the dynamic view of the static optimal transport. So the question is there a corresponding formula for the EOT function? So can I write this? EOT epsilon mu and nu by this similar formula. Is this clear? Okay, good. As you can see, of course, the original formula is not going to be true because it's exactly from W2 square mu to nu. You can also see that if there is a formula, then that formula should have a leading order term, which is the same as the W2 square, because as epsilon goes to 0, you expect the EOT cost function to actually converge to the Wasserstein 2 square cost function. So you expect that the leading order term should still be this kinetic energy. But then what you expect is that there should be some correction terms in terms a correction term which would involve higher powers of epsilon, which should vanish as epsilon goes to 0. Anybody wants to guess what this correction term is? Not that you can guess, but this is a term that you may be able to guess. You have seen this before. So just to think about it, would you take a guess? Anybody?
Intuitively, we'd have some sort of Laplacian operator that's showing up for the entropy term.
Some sort of Laplacian. That's a good thing. It's not quite Laplacian, but think of one object which you have seen repeatedly come up whenever we are dealing with entropy. Some term which repeatedly comes up whenever we are dealing with entropy.
Like the Fisher
Like
information.
from the very good Fisher information, exactly. So the term that actually does come up has to do with Fisher information. And so I'm going to write down this formula. Okay. So this requires a little bit of regularity on mu and nu, which I am putting under the rag. So I will post some papers there. You can check this. So this requires some regularity on mu and nu. We don't know if they're tight. They're probably not. So you expect some regularity. But what you get from here is that this is infimum of, again, rho t vt. And then what you will get here is that this is, the first term is just the same, vt square L2 square rho t dt. The second term is going to be epsilon over 2 entropy of mu plus entropy of nu. And the third term is going to be epsilon square over 8 integral from 0 to 1. Now this is the Fisher information coming here. So I of rho t dt. So what is I of rho t? Is the integral of the L2 norm of the gradient of log of rho t norm square d rho t. All right. So that's a full form. That's a full form of the Benamo-Brenier with this entropy regularization cost function. That you get. What you get is that this part actually doesn't depend on the infimum. You can just pull this out. This is just saying that there's a term which is the entropy of the first entropy of one marginal plus entropy of the other marginal that comes with a factor of epsilon over 2. But this doesn't really enter into the infimum. What the infimum really encounters is a kinetic energy, which was exactly as before. But then what it has is this epsilon square plus 8 times the integrated Fisher information over this curve that you get. And that's a new term that you get from here. One of the advantages of this is the following expansion of the EOT cost function. So here's a theorem that if I look into the EOT cost function mu and nu, I get this is equal to W2 square from mu to nu. Actually, again, I'm sorry, I have to account for that 1/2. This is the whole reason why this is confusing. So the EOT, I'm putting a 1/2 here. So I should put a 1/2 everywhere. So this should come with a 1/2. And so I would get that this is 1/2 W2 square. That's coming for the first term. Now the second term will remain exactly the same. So this is epsilon over 2 entropy of mu plus the entropy of nu. And then the next term that you will get from here is epsilon square over 8 integral of I of rho t star dt from 0 to 1, where rho t star for 0 between 0 and 1 is the geodesic joining mu to nu. Okay. Now, why is this thing important? As I've mentioned multiple times, and from data, you can essentially only compute this guy. Okay, so you can only compute the EOT cost function because that's what your IPFP or your synchron algorithm lets you do. You can also run a full linear programming. It's just prohibitively expensive and suffers from curse of dimensionality. So if you only learn this entropy regularized cost function, but what you're actually interested in is the Wasserstein cost of transport, you need to know how much error you're making. And this gives a very clean decomposition of the error up to first 2 powers of epsilon. They're saying that the first power of epsilon, so epsilon times a term which doesn't depend on the geometry at all. It's very simple. It's a sum of the average of the 2 marginal entropies. So the more entropy there is in your distribution, the more error you're going to make. Okay, that comes to the power of epsilon. The second one, which comes to the power of epsilon square, is more complex. What it says that you need to know the geometry to calculate this error. This is like you look into the geodesic that is joining mu to nu, and you look into its Fisher information along that geodesic. You integrate it out from 0 to 1, and that's the other term that you're getting. And so I should also say that this is plus little o of epsilon square. Okay, we don't know the full thing, of course. This is the expansion that we get. Okay, is the statement of this theorem clear? Okay. How do I guess this result from this new Benamou-Brenier formulation? Is actually quite easy. You see, if you look into this expansion of the EOT cost function as this kind of, this variational way, and you ask where is this infimum achieved? Now the leading order term is the same as the original Benamou-Brenier. Now I know where this is actually minimized. It's minimized at the geodesic. And so your first intuition should be that this infimum should be roughly where I take the leading order term to be the same as the geodesic, and then I compute this correction term over the geodesic. And then you actually push through the argument of analysis to show that this intuition is actually correct. Do you understand what I'm trying to say? Because the leading order term is the same as that of Benamou-Brenier, I know that the Benamou-Brenier is minimized at the geodesic. So you take this line, and now you say, okay, now let's just apply the correction terms to that particular one. And that gives you this formula. And then you argue that this is the best thing that you can do with some analytic arguments or limiting form as epsilon goes to 0. This is the best that you can do. And that gives you this theorem. Any questions?
I'm sorry, could you explain that philosophy one more time? So you said for very small epsilon, it's approximately a geodesic, and then you have
right. So
right,
exactly. So then you do a first order variation for very small epsilon. This infimum is essentially being controlled by infimum of the kinetic energy term, and I know where the infimum of the kinetic energy term is. That's at the geodesic. And so if I want to account for the correction terms, my first order of correction would be, well, let's take the infimum of the leading order term, and let's add the correction term applied to the leading order term, and that's this object. And then you show that this is essentially the right thing to do. Make sense? I mean, this is a general principle you can apply to other optimization problems. You have a function which is fx plus epsilon times g of x, and you're trying to minimize this as epsilon goes down to 0. If you know where is the infimum of fx, then your first guess as epsilon goes to 0 would be, well, let's take that infimum of fx, apply it to f plus epsilon g, And that should give me a very good approximation of what this infimum is. Okay. And then you apply some analysis to show that this is the right thing to do. But that should be your first guess. Okay. All right, good. There is one more way. There is another way to see how this theorem is true. So one proof of this is by this Benamo-Brenier. But there is a more probabilistic way to see why this theorem is true. And that is like trying to come up with a Gaussian approximation of the Schrodinger bridge itself. To the Schrodinger bridge itself. So what does that mean? It means that if I look into my Schrodinger bridge, gamma epsilon star xy, I know it looks like this, e to the power minus 1 over 2 epsilon, norm of y minus x norm square, minus a epsilon of x over epsilon, minus b epsilon of y over epsilon. I know that it looks it as this one giant density. I also know that I can write it as mu x times some p epsilon xy, where this is some kind of transition density. How can I write it? Because I know gamma epsilon star is a coupling of mu and nu. So I can separate out what is the x, the marginal of x, that is mu x. And if I divide by mu x, whatever remains is p epsilon xy, by definition, is a transition density. And so one can ask like, okay, how does this transition density look like? And the result is that this transition density is approximately Gaussian. So here is another idea. So here's another result. Again, this requires assumptions that I'm kind of sweeping under the rag, under assumptions that this p epsilon xy is Gaussian. So what do it mean? It means that it's a normal distribution. It's normal. Now it has a mean and a covariance matrix. Now the mean matrix is actually given by the Brenier map. So gradient of phi of x, where gradient of phi push forwarding mu to nu is the Brenier map. Good, so that's the mean. So mean, it is approximately Gaussian, where the mean is exactly where Brenier is trying to take you. But it has a covariance matrix. And what is this covariance matrix? This is epsilon times the Hessian of phi of x inverse. Okay, so this is the Hessian of phi. This is a positive definite matrix. Okay. Okay, so my Hessian this is a positive definite matrix. Is PSD because it's a convex function, and you look into its inverse, multiply by epsilon, and that's a covariance matrix that you get from this. If you take this Gaussian density, and now this is not an exact description. This is only approximately true, because under this Gaussian density, you don't have the right marginal. You only have one marginal is mu, the second marginal is not nu, but this is a good enough description for which actually you can recover the first two terms of this expansion. The third term requires more work. Does this make sense? So the Schrodinger bridge, we know that this is approximately Gaussian. And it's Gaussian, which has a mean, which is where Brenier is taking you, but then it has a tail. And this tail depends on the sensitivity. And the sensitivity, it comes with a factor of epsilon. So it's going down to 0 as epsilon goes to 0. But then its covariance matrix is the inverse of the Hessian of the Brenier. Right? Okay, good. Now, let me see a little bit. Any questions on this one? Okay, good. Let me talk a little bit about statistical part of this. Give me 1 second. Give me 1 second, sorry. Okay, let me talk a little bit about computational and statistical issues. And okay, why can I not find this? Okay, sorry, guys, I just need to find my notes here. Okay, good. So the basic problem comes in statistical and computational issues is that if I have n data points, if I have n IID data points from, let's say, 2 distributions from mu and nu, can I compute, let's say, W2 distance between mu and nu? And how complex is this computation? Is this computation? Now, if you now solving an optimal transport, so your first instinct should be that let's try to compute this optimal transport on these n data points. So I have these 2 distributions, mu hat n, which is 1 over n, the sum of delta mass at xi, from I equals to 1 to n, and nu hat n, which is the sum over 1 over n, j equals to 1 to n, delta of yj. So I have these 2 purely atomic distribution. I can try to compute what is W2 distance between mu n hat and nu n hat. And I can ask if this is actually converging to W2 distance between mu and nu. How will I compute the first thing? I will compute this first thing by doing my linear LP problem, my linear programming problem. This would be my naive approach to doing any of this linear programming problem. Now, several things that were observed. One is that if you do your linear programming on these n data points, so LP on these n data points, its complexity, this number of operations that you require here, is O tilde of n cube. So leaving my log terms and so on, this is roughly, it will take you n to the power cube, many such terms. On the other hand, if for every positive epsilon, if I compute my EOT cost function, my EOT epsilon can be computed in order of about n square. So as you can see from here, that for every positive epsilon, I get a massive reduction in computational complexity from n cubed to n square. And this is essentially by using synchron. This is what Marco Couturi's algorithm does. Let's use synchron, make a parallel computation, just doing matrix computations. Things are much simpler. Okay. We can also ask about what happens to this convergence. So I'm going to write out a chart here. Sorry,
Just to clarify,
Yes.
are these measures like, what's the background space? Are we working in R? Measures on
This
R
is over
or
any RD. Yeah, take
over
any
any
RD.
RD?
There's even a worse factor of dimension here, which I'm just ignoring.
Okay.
Is over RD. It doesn't matter. When you're working with discrete data, it doesn't matter whether you're working with RD or any other abstract space. Essentially, all that matters is what is the pairwise cost of matching any xi with any yj. So even with infinite dimensional spaces, they're just the same. It doesn't really matter whether it's RD or not. Right? All that matters is what is the cost C applied to xi when xi goes to yj, what is the cost C of xi yj? So it's a matrix of numbersCij's, and you're trying to give the optimal matching of all them. So it doesn't really matter what space you're working on. But if it helps, just take them to be RD. Make sense? In the next part of the statement, the space does matter, but for finite computations, it doesn't.
Maybe I'll ask more about this after the lecture.
Sure. Okay. So the EOT can be computed in this. So for the computing the EOT, of course, you need the space because you need to construct the Brownian transition density, which does involve this norm of xi minus yj squared. But again, this can also be done for any cost function. Doesn't really matter. Yeah. For the other problem, it is that, well, how fast does this converge? This W2 mu n hat nu n hat, this convergence to W2, this does converge to mu to nu. This is painfully slow. This is of the order of n to the power of 1 over d. So, or rather, I should say, yeah, so it's order of n to the power of minus 1 over d. So this is the rate at which it's converging. So when d is, let's say, 50, you're working on some 50-dimensional data, it's essentially you need a gigantic amount of data to actually compute. On the other hand, you can show that if the marginals, if mu and nu are nice, let's say here sub-Gaussian, then for every fixed epsilon, each fixed epsilon, your EOT, which is what you compute from data, okay, why is this slow? So EOT, which you compute from your data on mu n hat and nu n hat, this will converge to EOT mu and nu. This is of the parametric rate of order of n to the power minus 1/2. Now, I should again warn that these are this big O actually hides a function of epsilon, which is really bad. But if epsilon is fixed, we recover a parametric rate. And so this again goes back to my point of that you want to understand how much does your EOT vary along the actual optimal transport, because often in practice, it is easier to either compute or estimate what is the entropy regularized cost rather than the true optimal transport cost. Okay. I will also, next time I'll talk more about synchron iterations, synchron's rate of convergence, but I also want to mention a little bit here. 1 second. Oh, so we can also ask, for example, do we know of central limit theorems? Are there central limit theorems which are true for these estimates? So surprisingly, you can't prove central limit theorems for this guy. It has a bias which is pretty bad. This doesn't actually work, but very recently the central limit theorem for this guy actually has been proved. So this guy also converges nicely, and also you can have like Gaussian confidence intervals built around them. That's about the extent I want to say here. So known for EOT. Much more interesting statistical questions are, for example, can I estimate what is the optimal transport map, which is not the cost? And there two things are also known. In general, there are many algorithms that you can build. Some of them are based on entropy regularized optimal transport, some of them are not. And the best that you can hope for is this parametric rate if they attain that rate. But they all require some kind of regularization. Without regularization, you can't have good rates of convergences. All right, okay. Now, our final thing today, I want to talk a little bit about rates of convergence of synchron. So rates of convergence of, I would say IPFP, really, but generally everybody calls it either IPFP or synchron. So as I said, what you're really interested in is really rates of these convergences as epsilon goes down to 0. So for small values of epsilon, because that's where you're actually trying to compute these things. And there, things are not as nice as one would expect. So for every positive epsilon, and there is a bunch of recent work which has been done, that for every positive epsilon, if epsilon is positive, is fixed under nice tail assumptions of mu and nu, we get that there are these convergence rates of synchron. Synchron will converge at an exponential rate. Okay, synchron converges an exponential rate. My iPad has now frozen. Okay, 1 second. Okay, so let me just say what I'm trying to say here. So when mu and nu are very nice densities, so some nice tail distributions that are there, then we know that synchron will converge for every fixed epsilon at an exponential rate. So exponential convergence. And these typically come in the form in terms of iteration. So after n iterations, your convergence is like, so this is some unknown constant, and this is kappa is some number between 0 and 1, and n is the number of iterations. So they would say that there is some constant c epsilon and some constant kappa, which is between 0 and 1, So that if you run your synchron algorithm for n steps, then what you get is a convergence which is measured either in relative entropy or Warshaw distance. This is of the form C epsilon kappa to the power n. This is great because I get an exponential convergence in my iteration step. However, this constant C epsilon is really bad. It's like e to the power of some polynomial in terms of 1 over epsilon. This explodes super exponentially. What would be really nice to have is to have when does exponential convergence hold for all small enough epsilon? Or to come up, which is actually it is known in practice that it is not true for all mu and nu. There are mu and nu where this is slow. So corresponding question would be that when is it slow? When does it not converge exponentially fast for all small enough epsilon? These questions are still rather open. Only like a couple of 2-3 papers have appeared in very recently in the last 2 years. I will talk about one of them the next time, but this is a big area of research. That if you look into synchron, what can I say about rates of convergences given the 2 information and the 2 marginals? What can I say about the rate of convergence for small enough epsilon? All right. Okay. So next time I'll talk about one such paper which talks about what is the geometry underlying this convergence, but that's for Friday. Okay. Any questions?
Okay, so I guess we have to this question. I think I'll figure it out why it was.
I'm sorry, I cannot hear you clearly.
Oh, yeah, I asked about the dimension of the background space. I think I figured out what my confusion was. So
Okay, yeah. So as I said, for finite data problem, the background doesn't matter. It could be anything. All you have is a matrix Cij.
right. Yeah, exactly. Okay. Yeah, I was thinking we'd have to build some sort of tensor, like based on the dimension of space, but yeah, you just build
It's just a matrix.
just a matrix, right?
Yeah, it's just an n by n matrix Cij. And then you run either a perfect matching or you run your synchron. Okay, any other questions? All right, okay. So if not, we'll see you on Friday and we'll talk about the geometry behind the synchron convergence. Okay. All right, see you guys later. Sorry.
Is there a good reference for this dynamic formulation? I've read Marcel Nutz's notes. I don't think that this.
No,
dynamic
Marcel Nutz's
formulation.
note, he doesn't talk about the dynamic formulation. I'll post it on, I will post it on Slack.
Thank you.
Okay. Right. Okay. Bye.